Let's look at the next example problem, which is edge click cover. So what's an edge click cover? So you know what a clique is, right? So it's a set of vertices that are all pairwise adjacent. Now, an edge click cover is a set of cliques that covers all the edges of the graph. So every edge of the graph must be inside at least one of the cliques that we selected. So we're going to select cliques, and an edge is covered by a clique if it's completely inside this clique. And now the size of an edge clique cover is the number of cliques that we selected. So in the edge clique cover problem, we have as input a graph G and an integer k. The parameter is k, and the question is whether G has an edge clique cover of size at most k. So whether there's at most k cliques that cover all the edges of G. Okay, let's go through a few helpful properties. So we will say that the clique in a graph is a maximal clique if it's not a subset of another clique, so a strict subset. So we'll also call this maximality inclusion-wise maximality. Now our lemma says that a graph G has an edge clique cover of size at most k, if and only if it has an edge clique cover of size at most k, where every clique is a maximal clique. So I'm proving this is quite simple. So if we start from an edge clique cover C, we can transform it into an edge clique cover C prime, where each clique is a maximal clique, just by replacing each clique by a maximal clique that contains the first clique. And the reverse direction is trivial since C prime is an edge clique cover of size at most k. Okay, so we can assume that each clique that we select into our edge clique cover will be a maximal clique. Okay, now again, we will imagine a very large instance where the parameter is tiny. And then we ask, how can you simplify such an instance? Okay, so let's assume our parameter is 3. So we have, if we have a yes instance, then there exist 3 cliques that cover all the edges of the graph. Okay, now we just check where are the vertices contained. So the vertices, well, there's no vertex outside here because, or actually there might be. There might be vertices out here, but they don't occur in any clique. Well, all the edges of the graph are inside the cliques, right? So these are all degree 0 vertices. So that means that they all have degree 0. We will never add them to a clique to cover edges because they're not useful. Okay, so all the remaining vertices are now inside these cliques. Let's see. So let's take 2 vertices, like let's say vertex A and B, and let's see how they look like. What is their neighborhood like? So they are adjacent because they are together in one clique. Well, they're actually adjacent to everybody else in this clique. And this vertex, that vertex, this vertex, and that vertex. Who else is neighboring A or B? Well, nobody, right? Because, well, if we had this edge, for example, then it wouldn't be covered by any clique, so this edge doesn't exist. Okay, so we can observe that, well, actually, A and B have the same neighborhood. Because they are exactly in the same cliques, we know exactly which neighbors they have. they are adjacent to everyone that occurs in the same cliques, in the same clique. If they would be in multiple cliques, then again they would be adjacent to everybody in those cliques and to nobody else. So that's the case also for vertices that are in multiple cliques, like this one. So it will be adjacent to all the vertices that are in the same cliques and to nobody else. So if we have two vertices that occur in exactly the same cliques, then we know that they have the same neighborhood. Okay, so since our parameter is tiny, but number of vertices is huge, we know that there must be two vertices that occur exactly in the same cliques. But then they should have, so we know that there's two vertices at least, or multiple vertices, with the same neighborhood. Can we do something about those vertices? So let's say a pair of vertices that have the same neighborhood. And it turns out we can, because, so let's say we cover all the edges that are incident to one of them by cliques. But now adding the other vertex to exactly the same cliques then also covers the edges of the other vertex. So what we can do is, well, delete B from the graph, solve the instance. So if we have an edge clique cover for the graph that doesn't contain B, we can always get an edge clique cover for the graph that includes B by just adding B to exactly the same cliques that contain A. Because A and B look exactly the same, and they are adjacent, so adding B to the same cliques as A will produce an edge clique cover for the graph. And we can do the same for this vertex down here, because, well, it's also contained in the same cliques as A. Okay. So these are our simplification rules. So first of all, if there's a vertex with degree 0, we remove it from the graph. And so that simplification rule is sound because, well, there's no edge incident to that vertex. So a smallest edge clique cover for G minus V is a smallest edge clique cover for G, and vice versa. There's one rule that I forgot previously when we went through the example. If there's actually two adjacent vertices with degree 1, so we have two vertices U and V, both of them have degree 1, so there's no other vertices adjacent to U and V. So in that case, we cannot do what I just proposed because, well, what I proposed was, well, delete one of the two vertices, solve the instance for the other one, and now add, let's say we deleted V. Now, in the end, add V to all the cliques that contained U. But by doing this, deleting V, now U gets deleted by the first rule, and so U will not be in any clique. So we need to handle this special case, and that's why we have this isolated edge rule, where we basically we will have one dedicated clique just to cover the edge UV. We need to cover it, and the only clique that covers it is the clique UV. Okay, so now in this special case, if both endpoints of an edge have degree 1, we remove the two vertices and we decrease k by 1. And the next rule is the twins rule. So two vertices are twins, or true twins, if their closed neighborhoods are the same. So they are adjacent to each other and they have the same neighborhoods outside of U and V. So if there's two distinct vertices U and V with the same closed neighborhood, then we remove one of these two vertices. So now the lemma is sound, assuming that the previous rule did not apply. So we usually state our simplification rules in the order that they are applied. So we first apply the isolated vertex rule exhaustively until it cannot be applied anymore. Then we apply the isolated edge rule. So after applying it, we check again whether the isolated rule applies. If not, then we check for the isolated edge rule. If that one doesn't apply, we then check for the twins rule. And now the twins rule is sound. And for this, we need to show that G has an edge clique cover of size almost k, if and only if G minus V has an edge clique cover of size almost k. So if C is an edge clique cover of size almost k, then just removing V from every clique in that edge clique cover gives us an edge clique cover of G minus V of size almost k. Now, if we have an edge clique cover of G minus V of size almost k, then, well, we can partition the cliques into two sets. So first of all, we have those cliques that contain U, and then we have those cliques that do not contain U. Now, for every clique that contains U, we add V also to those cliques. And for those cliques that didn't contain U, we just leave them alone, we just copy them over. And so when we add V to those cliques that contain U, this will again give us a clique, since the neighborhood of U and the close neighborhood of U and G are the same. And so now we have that the set calligraphic C U and calligraphic C prime minus U is an edge clique cover of G of size almost k. Okay. Our next simplification rule is now again a size restriction. So we said that if the previous simplification rules do not apply and the number of vertices is more than 2 to the power k, then we return no. And I claim that size V is sound because, well, if the number of vertices is more than 2 to the power k, and we would have a yes instance, then necessarily we have at least two vertices that are contained in the exact same cliques. But we don't have twins anymore in our instance, so that's not possible. So to show that size V is sound, we assume that none of the previous simplification rules apply, and the number of vertices is more than 2k, and we have a yes instance. But since the set of all subsets of Z has size almost 2k, every vertex belongs to at least one clique in C, and we have that they exist. Well, then we must have two vertices U and V, such that the cliques that contain U equals the cliques that contain V. But then their neighborhoods must be the same, contradicting that the twin rule was not applicable. Okay, so we conclude that edge clique cover has a kernel with order 2k vertices, 2 to the k vertices, and order 4 to the k edges. Because again, the number of edges is at most the square of the number of vertices. And this was proven by Jens, Graham, and others in 2008. So we get a kernel with order 4 to the k edges, of size at most 4 to the k. Let me just point out one thing very quickly. So here the simplification rule again says return no. Let me go back to the definition of kernels. So the definition of kernelization was, or said that we should produce an equivalent instance of the same problem pi of size at most, of size bounded by a function of k. So we need to produce an equivalent instance of the same problem. But now we just said we return no. Is no an instance of the same problem? So what we mean by returning no is just we return a very small no instance of the problem, just to be consistent with the definition of kernelization. Okay. The other thing I want to point out is that, well, this theorem 10 here, it implies that edge clique cover is fixed parameter tractable. So what was fixed parameter tractable? So it said there's an algorithm that solves this problem in time f of k times a polynomial in n, where n is the instance size, k is the parameter. Okay, so theorem 10 gives us, well, in polynomial time, so it says that in polynomial time, so in this time, we can get an equivalent instance of size at most order 4 to the k. Okay, but it doesn't yet solve the instance. So how do you solve this instance? Well, now we have a 4 to the power k instance. We can use any brute force algorithm that solves it. And solving it, well, will take some time, but since the size of the instance is already bounded by a function of k, whatever algorithm we throw at it, as long as it solves the instance, its running time will only depend on k and not on n anymore, because the size of the whole instance that we obtain is bounded by a function of k. N doesn't appear anymore. So in polynomial time, in n to the order 1 time, we obtain some instance whose size depends only on k and not on the size of the original instance anymore. So now, whatever brute force algorithm we throw at it will take some function of k time. And then in total, we get this kind of running time. Okay, so, and this is a more general property actually. So if we look at any decidable parameterized problem, then the problem has a kernelization algorithm if and only if it is FPT. So for the first direction, we do exactly what we did now. So if we have a kernelization algorithm, then we run the kernelization algorithm, we obtain an instance whose size is bounded by a function of k, and then apply any brute force algorithm to it. So since pi is decidable, there exists an algorithm that solves the resulting instance. So we just use it and then obtain an FPT algorithm. The other way around, if we have an FPT algorithm for pi that has some running time, so let's say its running time is order f of k times n to the power c for some constant c. Now we do a case analysis. Just consider two cases. So first, assume that f of k is less than n. Okay, so f of k here is less than n. So if we look at this running time of the algorithm A, so f of k is less than n, so A has running time at most n to the power c plus 1. So we have a polynomial time algorithm that in this case just solves the instance. So A has running time order n to the c plus 1, But in this case, okay, so our kernelization algorithm solves the instance. If solving it returns yes, then it returns a trivial yes instance. If solving it returns no, then we return a trivial no instance. Okay, so this handles the case where f of k is less than n. If f of k is at least n, so f of k is at least n. So we need to design a kernelization algorithm. So for a kernelization algorithm, the instance size needs to be upper bounded by a function of k. Okay, so look at this. So n here, the instance size is upper bounded by a function of k. So we are done. So in this case, the kernelization algorithm can just output the input instance. Some people feel cheated by this proof, but believe me, it's correct. Okay, so there's some further reading here on kernelization, and we will go more into depth in a further lecture. See you next time.